March 1943. Inglewood, California. The North American aviation factory floor hums with the controlled chaos of wartime production. Amid the deafening clatter of riveting hammers and the acrid smell of welding torches, a 17-year-old mechanic named Thomas Blevins stands beside the skeletal frame of a P-51 Mustang. His hands, blackened with grease and oil, tremble slightly as he stares at the massive Rolls-Royce Merlin engine suspended above the airframe by chains. The installation manual lies open on a workbench nearby, its pages fluttering in the draft from the factory's massive ventilation fans. Blevins has been working 12-hour shifts for 3 months, installing engines into America's newest fighter plane. But today, something is different. The mounting brackets don't align the way they did yesterday. The propeller shaft angle's wrong. Confusion clouds his young face as he signals the crane operator to lower the engine. Metal meets metal with a grinding protest. Bolts thread into place where they shouldn't fit. And in that moment, through fatigue and misunderstanding, Blevins commits what should have been a catastrophic error. He installs the Merlin engine backwards. Yet within weeks, test pilots will report something impossible. This particular Mustang flies faster than any other P-51 in the fleet. It outruns Messerschmitts and Focke-Wulfs with ease. Engineers will scramble to understand why. And the answer will challenge everything they thought they knew about aircraft design. By early 1943, the air war over Europe had reached a critical juncture. American heavy bombers, the B-17 Flying Fortresses and B-24 Liberators, were conducting daylight raids deep into Nazi-occupied territory, targeting factories, rail yards, and oil refineries that fueled Hitler's war machine. But these lumbering giants, despite their defensive armament of up to 13 .50 caliber machine guns, were suffering catastrophic losses. German fighters, primarily the Messerschmitt Bf 109. This left a deadly gap, hundreds of miles where American bombers flew unprotected, vulnerable to coordinated Luftwaffe attacks. German fighter controllers quickly learned the limits of American escort fighters. They simply waited beyond the escort range, then pounced on the exposed bomber streams. The result was slaughter. On August 17, 1943, during a raid on ball-bearing factories at Schweinfurt and aircraft plants at Regensburg, the 8th Air Force lost 60 heavy bombers in a single day. 600 men killed, wounded, or captured. The mission planners knew they were sending men to their deaths. They also knew that without long-range fighter escort, the entire strategic bombing campaign might collapse. Air superiority over Europe hung in the balance, and with it, perhaps the outcome of the war itself. The Allies desperately needed a fighter that could fly deep into German territory, engage the Luftwaffe on equal terms, and still have enough fuel to bring the bombers home. That fighter would be the P-51 Mustang, but not in its original form. The early Mustangs, powered by American Allison V-1710 engines, performed beautifully at low altitude but struggled above 15,000 feet. The Allison engine lacked an efficient supercharger for high-altitude operations, exactly where the bomber war was being fought. The RAF had tested these early Mustangs and found them disappointing for European combat. They were fast and maneuverable down low, perfect for ground attack and reconnaissance, but nearly useless in the high-altitude battles over Germany. Then came a stroke of engineering genius that would change everything. British engineers at Rolls-Royce proposed marrying the Mustang's sleek, low-drag airframe with their legendary Merlin engine, the same powerplant that drove the Supermarine Spitfire. The Merlin featured a sophisticated two-stage, two-speed supercharger that maintained power output even at 30,000 feet. North American aviation quickly grasped the potential. They negotiated a license to build the Merlin in the United States under the designation V-1650, manufactured by Packard Motor Car Company. By late 1942, the first P-51B models with Merlin engines were rolling off the production line at the Inglewood factory. Performance tests showed results that exceeded even optimistic projections. The Merlin-powered Mustang could reach 440 miles per hour at 30,000 feet, faster than any German fighter in service. Its range, with external drop tanks, extended beyond 800 miles, enough to escort bombers to Berlin and back. But producing these aircraft at wartime scale meant training thousands of inexperienced workers, farm boys, women entering the workforce for the first time, teenagers like Thomas Blevins who had never seen an aircraft engine up close before Pearl Harbor. North American Aviation hired and trained assembly workers at a frantic pace. The Inglewood plant operated around the clock, 3 shifts churning out Mustangs as fast as materials arrived. Quality control inspectors checked critical systems, but with hundreds of aircraft in various stages of assembly at any given moment, errors were inevitable. Most mistakes were caught before an aircraft left the factory. A missing rivet here, a misrouted fuel line there, fixable problems. But installing an engine backwards seemed impossible. The Merlin was a complex piece of machinery, weighing over 1,600 pounds, with hundreds of connection points for fuel lines, oil lines, coolant hoses, electrical wiring, control cables, and exhaust manifolds. Installation followed a precise sequence detailed in thick technical manuals. First, workers prepared the engine mount, a sturdy framework of steel tubes welded to the fuselage structure. The Merlin attached to this mount at 4 points, secured by massive bolts torqued to exact specifications. The propeller shaft extended forward through the cowling, connecting to a reduction gearbox that drove the four-bladed propeller at optimal speed. Behind the engine, the coolant radiator system tucked beneath the fuselage in a streamlined scoop that both cooled the engine and generated forward thrust through careful aerodynamic design, an innovation that reduced drag and actually added a small amount of jet-like propulsion. Oil coolers, intercoolers, and air intakes all had to align precisely. The supercharger intake drew air from a dorsal scoop behind the cockpit. Exhaust manifolds channeled spent gases through stacks that protrusioned along the lower cowling sides, their placement calculated to avoid disturbing airflow over the wings. Every component had a specific orientation, a correct position. Installing an engine backwards would mean nothing fit properly. Fuel wouldn't flow, coolant wouldn't circulate. The propeller would spin in reverse. The aircraft couldn't possibly fly. Yet somehow, impossibly, Thomas Blevins managed it. The exact circumstances remain murky, filtered through decades and the fog of wartime secrecy. Blevins himself, interviewed years later as an old man, could never fully explain what happened that day in March 1943. He remembered fatigue, chronic, bone-deep exhaustion from working 12-hour shifts 6 days a week. He remembered confusion. The Merlin engine looked subtly different from the Allison engines he'd trained on, and the British engineering drawings used different conventions than American blueprints. He remembered pressure, supervisors constantly pushing for faster production, reminding workers that every day's delay meant more bomber crews flying without proper escort, more American boys dying over Germany. In that environment, mistakes happened. But this particular mistake should have been caught immediately. The propeller shaft faced the wrong direction. The reduction gearbox couldn't attach properly. Control cables ran at impossible angles. Yet somehow, through a cascade of improbable circumstances, the engine not only installed but passed inspection. Perhaps the inspector was equally exhausted, or poorly trained, or simply overwhelmed by the sheer number of aircraft requiring sign-off. Perhaps paperwork got mixed up, and another aircraft's approval was mistakenly applied to this one. Whatever the reason, P-51B serial number 43 to 24760 left the factory floor with its Merlin engine installed backwards and was approved for flight testing. And that's when things became truly strange. Test pilot Robert Chilton climbed into the cockpit on a clear morning in late March. He'd flown dozens of Mustangs through their acceptance tests, standard procedures to verify all systems functioned correctly before delivery to combat units. Engine start, taxi, takeoff, climb to altitude, run through various power settings and maneuvers, check control response, land, and sign off. Routine. But from the moment Chilton advanced the throttle for takeoff, he knew something felt different. The acceleration was sharper, more urgent. The Mustang leaped off the runway with unusual eagerness. Climbing through 10,000 feet, Chilton pushed the throttle to combat power and watched the airspeed indicator climb past numbers he'd never seen in a Mustang before. At 25,000 feet, the indicated airspeed read 460 miles per hour, 20 miles per hour faster than the P-51B's rated maximum speed. Chilton was experienced enough to know this wasn't instrument error. The aircraft felt faster, responding to control inputs with crisp immediacy. He pushed it harder, diving to build speed, then pulling up into a steep climb. The Merlin engine sang at high RPM, its supercharger forcing compressed air into the cylinders with seamless power delivery. Leveling off, Chilton ran speed tests at different altitudes. At every measurement point, this particular Mustang flew faster than any other P-51B he'd tested. Significantly faster. He landed with his mind racing through possible explanations. A particularly efficient propeller, an engine that happened to produce slightly more power than rated, exceptional build quality that reduced drag. He couldn't explain it, so he did what any puzzled test pilot would do. He wrote a detailed report noting the aircraft's unusual performance and recommended further investigation. Engineers descended on P-51B number 43 to 24,760 with calipers, measuring tapes, and notebooks. They examined the airframe for anomalies, checked wing contours for irregularities, measured panel gaps and surface smoothness. Everything appeared normal. They pulled the cowling to inspect the engine installation, expecting to find some clever field modification or manufacturing variants that might explain the extra speed. And that's when they discovered Thomas Blevins' impossible error. The Merlin engine sat backwards in its mounts. The propeller reduction gearbox faced rearward. Control cables looped in directions they were never designed to run. Coolant lines followed circuitous paths to reach their connections. It was an engineering absurdity, a mechanical impossibility that somehow not only worked but worked better than the correct installation. The engineers stared in disbelief. Senior aeronautical specialists were summoned. Calculations were performed and reperformed. Wind tunnel models were proposed. And slowly, reluctantly, an explanation emerged that challenged fundamental assumptions about aircraft propulsion and aerodynamics. The backwards engine installation had inadvertently created a more efficient airflow pattern through the engine compartment and around the fuselage. The reversed propeller rotation changed how air moved over the wings. The rerouted exhaust manifolds expelled gases at slightly different angles, creating marginally more thrust. The repositioned coolant radiator scoop, forced to mount differently due to the backwards installation, happened to generate less drag and more cooling thrust than the standard design. Each small change, individually insignificant, combined into a measurable performance improvement. But there was more, something even the engineers initially missed. The backwards propeller rotation had a profound effect on the aircraft's handling characteristics, particularly in high-speed flight and during maneuvers. A propeller spinning clockwise produces torque that tries to roll the aircraft to the left, requiring constant right rudder input from the pilot. The P-51B's propeller normally rotated in the same direction as most Allied aircraft, a convention established early in aviation history and rarely questioned. But German fighters, the Messerschmitt Bf 109 and Focke-Wulf FW 190, used propellers that rotated in the opposite direction due to different engine designs. When two aircraft engaged in a dogfight, propeller torque influenced their turning performance. A Mustang turning left fought against its propeller torque, making the turn slightly slower and mushier. A Mustang turning right turned with the propeller torque, making it sharper and faster. German fighters had the opposite characteristics. In combat, pilots learned these quirks and exploited them. But with the engine installed backwards, P-51B number 43-24760's propeller now rotated in the same direction as German fighters. Its turning characteristics reversed. Left turns became sharper. Right turns became mushier. For an American pilot accustomed to standard Mustang handling, this would be disorienting. But what if a pilot trained specifically on this backwards engine aircraft? What if the reversed handling actually proved advantageous in combat against Luftwaffe fighters? These questions sparked intense debate among engineers and tactical planners. The implications were staggering. If installing the engine backwards genuinely improved performance, should all Mustangs be built that way? But reversing the standard configuration would require redesigning hundreds of components, retraining thousands of workers, and potentially delaying production by months, time the 8th Air Force didn't have. Bomber crews were dying over Germany right now, today, this week. Every day without adequate fighter escort meant more losses. Production delays were unacceptable. Yet if this configuration offered even a 5 or 10% performance advantage, it could mean the difference between life and death in combat. A faster Mustang could catch German fighters that might otherwise escape. A more maneuverable Mustang could outfight opponents in close-range dogfights. The calculations became grim arithmetic. Would the lives saved by improved performance outweigh the lives lost during production delays? There was another problem. The backwards installation, while functional, was still fundamentally wrong. It stressed components in ways they weren't designed to handle. Fuel lines bent at sharp angles. Coolant hoses stretched across excessive distances. Control cables ran over pulleys at inefficient angles, increasing friction and wear. The engine might perform brilliantly now, but what about after 50 hours of operation? 100 hours? Would premature failures plague this configuration? Would maintenance prove impossibly difficult in field conditions? The engineers needed more data. They needed flight testing under controlled conditions. They needed to know if this accidental innovation was a genuine breakthrough or a dangerous fluke. And so began one of the strangest experimental programs in aviation history. a program so sensitive that it remained classified for decades after the war. P-51B number 43 to 24760 became the subject of intensive testing at Wright Field in Ohio, the Army Air Force's primary testing facility. Pilots flew it in mock dogfights against captured German aircraft, a Messerschmitt Bf-109G and a Focke-Wulf FW-190A that had fallen into Allied hands through defections and forced landings. The results were eye-opening. Against the Bf-109G, the backwards-engine Mustang demonstrated superior speed at all altitudes and could outmaneuver the German fighter in sustained turning engagements. The Messerschmitt pilot, a Luftwaffe defector flying for the Allied test program, reported that he felt consistently disadvantaged, unable to escape when the Mustang pursued and unable to gain an advantageous position when the Mustang evaded. Against the FW-190A, the results were even more pronounced. The Focke-Wulf was a formidable opponent, feared by Allied pilots for its powerful BMW radial engine, heavy armament, and excellent roll rate. But the backwards-engine Mustang matched it in speed, exceeded it in climb rate, and, most surprisingly, could reverse direction in a rolling scissors maneuver faster than the German fighter. The test pilots wrote reports describing combat scenarios where the reversed propeller torque actually helped the Mustang reverse direction more aggressively, confusing opponents who expected standard handling characteristics. One report noted, "The enemy pilot anticipates our turn performance based on experience with standard Allied fighters. When we instead demonstrate reversed handling characteristics, his tactical assumptions become liabilities. He misjudges our turn radius and reversal timing, granting us firing opportunities he inadvertently creates." This was revolutionary. For the first time, engineers and tacticians began discussing not just the backwards engine's performance benefits, but its potential as a psychological weapon. If a small number of Mustangs with reversed engines deployed alongside standard P-51s, German pilots wouldn't know which aircraft they faced until engaged in combat. The uncertainty would force them to fight more cautiously, reducing their effectiveness. The Luftwaffe's carefully developed tactics, honed through years of combat, would become unreliable. But there was a darker side to this innovation, one that Air Force leadership couldn't ignore. If word of the backwards-engine Mustang reached Germany, Luftwaffe engineers might analyze captured aircraft or wreckage and realize the potential. They might reverse their own engines, creating German fighters with unexpected handling characteristics. The tactical advantage would vanish, replaced by even more confusion and unpredictability in combat. Worse, if Germany developed better methods of exploiting reversed propeller rotation, they might gain an advantage over standard Allied fighters. The Air Force faced a strategic dilemma: exploit the backwards engine design and risk Germany copying it, or suppress the innovation to maintain the status quo. The decision came down from the highest levels. A limited number of P-51Bs would be intentionally built with backwards installed engines, never enough to impact production schedules, but enough to field test the concept in combat conditions. These aircraft would be assigned to experienced pilots who could adapt to the reversed handling and exploit its advantages. The program would remain classified. Even the pilots wouldn't initially know why their aircraft handled differently, they'd be told only that they were testing experimental modifications. 6 pilots were selected from the 354th Fighter Group, the first 8th Air Force unit to receive P-51Bs. These men were veterans with multiple combat missions and confirmed kills, trusted to handle unusual aircraft and maintain operational security. They received their backwards-engine Mustangs in April 1943, coded with innocuous serial numbers that didn't reveal anything special. The aircraft looked identical to standard P-51Bs, with one subtle marking: a small inverted triangle painted under the cockpit, supposedly indicating test configuration, but actually marking them as backwards engine variants. The pilots flew them on training missions first, familiarizing themselves with the reversed handling characteristics. Initial reactions were mixed. Some pilots found the different torque effects disorienting, fighting ingrained instincts developed over hundreds of flight hours. Others adapted quickly, appreciating the sharper left turns and finding ways to exploit the unfamiliar handling in mock dogfights. One pilot, Captain Robert Johnson, wrote in his personal diary, "The new ship feels wrong at first, like wearing your boots on the wrong feet. But after a few hours, you start to understand her. She wants to turn left harder than any Mustang I've flown. In a scissors fight, I can reverse faster than guys in standard birds expect. It's like having a secret weapon they can't see." By May 1943, the 6 pilots and their backwards-engine Mustangs deployed to operational status, flying escort missions over France and the Low Countries. The results were immediately apparent. On May 14, 1943, Captain Johnson flew escort for B-17's bombing U-boat pens at L'Oreal. Approaching the target, Luftwaffe fighters bounced the bomber formation, 12 Focke-Wulf FW-190s diving from above with textbook precision. Johnson's flight engaged, and the sky erupted into swirling chaos of tracer fire and screaming engines. A FW-190 latched onto Johnson's tail, hammering .50 caliber rounds that sparked off his armored headrest. Johnson broke left, harder than any standard Mustang could turn, the backwards engine installation loading the wings with G-forces that would have stalled a normal P-51B. The Focke-Wulf pilot, expecting a wider turn radius, overshot and flashed past Johnson's nose. Johnson rolled inverted, pulled through, and found himself on the German's tail, a position reversal that took less than 3 seconds and violated every energy management principle the Luftwaffe pilot had learned. Johnson pressed the trigger, his 6.50 caliber machine guns converging streams of fire into the FW-190's engine cowling. The German fighter shuddered, trailing black smoke, and dropped away in a steep dive. Johnson didn't follow, instead climbing back to the bomber formation. But he'd seen something crucial, his opponent's confusion in that critical moment when the Mustang reversed direction faster than expected. The German pilot hesitated, just a fraction of a second, trying to process flight characteristics that didn't match his experience. That hesitation cost him his life. Over the following weeks, the 6 backwards engine Mustangs compiled a startling kill ratio. Between them, they shot down 23 German fighters by the end of June, nearly 4 kills per aircraft in just 2 months. Standard P-51Bs averaged about 1 kill per aircraft over the same period. Something was clearly working. But the program also revealed problems. The backwards installation stressed components exactly as engineers had feared. Fuel pumps failed prematurely. Coolant hoses developed leaks. Control cables stretched and frayed, requiring frequent adjustment. Maintenance crews, initially confused by the reversed configurations, needed special training to service these aircraft properly. Ground time increased, hours of maintenance for every flight hour, well above the norm for standard Mustangs. One backwards engine Mustang suffered catastrophic engine failure over the English Channel, forcing the pilot to bail out. He was rescued, but the aircraft sank before engineers could examine the wreckage to determine if the backwards installation contributed to the failure. Another crashed during landing when a hydraulic line, stressed by its unusual routing, burst and locked the landing gear in a partially extended position. The pilot survived with minor injuries, but the aircraft was destroyed. These incidents sparked fierce debate within the Air Force. Some argued that the performance advantages justified the maintenance headaches and occasional failures. Others insisted that reliability was paramount. That an aircraft in the maintenance hangar helped no one, no matter how fast it flew when operational. The argument intensified when engineers presented data showing that the backwards engine configuration, while faster in straight-line flight and more maneuverable in certain conditions, actually performed slightly worse in other critical areas. High-altitude ceiling was reduced by about 1,000 feet due to less efficient supercharger airflow in the reversed configuration. Acceleration at low speeds was marginally worse. And fuel consumption increased slightly, reducing combat radius by perhaps 20 miles. These weren't crippling disadvantages, but they complicated the calculus. Was a Mustang that was 5% faster but slightly less reliable and with slightly reduced range actually superior to a standard P-51B? Or was the backwards configuration a fascinating but ultimately impractical experiment? The debate became moot in August 1943 when catastrophe struck. Captain Johnson, the backwards engine program's most successful pilot, was escorting B-17s to Schweinfurt, the same mission that would see 60 bombers lost in a single day. Over central Germany, his flight engaged a large formation of Bf-109s and FW-190s. Johnson maneuvered aggressively, exploiting his Mustang's reversed handling to outfight 3 German aircraft in succession. He shot down 2 Bf-109s and damaged a FW-190 so severely it broke off trailing smoke. But in the furious combat, he pushed his engine beyond redline limits, demanding maximum power for sustained periods. The backwards installation, already stressed by its unconventional component routing, couldn't handle the punishment. A coolant hose ruptured, spraying superheated liquid across the engine compartment. Within seconds, coolant temperature gauges spiked into the danger zone. Johnson had to make an immediate decision: try to limp back to England on an overheating engine that might seize at any moment, or bail out over enemy territory. He chose to stay with the aircraft, nursing the throttle, watching the temperature gauge hover at the edge of catastrophic failure. He crossed the English Channel at low altitude, barely maintaining airspeed, and crash-landed at the first airfield he could reach, a small RAF station on the Kent coast. The Mustang's landing gear collapsed on touchdown, and the aircraft skidded to a halt in a shower of sparks and torn metal. Johnson climbed out shaken but unhurt. But his backwards engine Mustang was finished, too damaged to repair. More critically, the incident forced a reckoning. If even the program's most skilled pilot nearly died due to the backwards installation's reliability problems, could the Air Force justify continuing the experiment? The answer came down from General Henry Hap Arnold, commanding general of the Army Air Forces. The backwards engine program would be discontinued. The remaining 5 special Mustangs would be returned to standard configuration. The tactical advantages, while real, didn't outweigh the maintenance difficulties and reliability concerns. The Air Force needed fighters that could be mass-produced, maintained by mechanics of average skill under field conditions, and flown reliably day after day by pilots of varying experience. The backwards engine Mustang was a fascinating innovation, but it was also a logistical nightmare. Mass production and standardization won over boutique performance. Thomas Blevins' accidental innovation would be forgotten, buried in classified files. Except the story didn't end there. Because while the backwards engine Mustangs were being returned to standard configuration, engineers at North American Aviation and Rolls-Royce had been studying exactly why the reversed installation performed better. They identified specific improvements that could be incorporated into standard Mustangs without reversing the entire engine. Modified exhaust manifolds that expelled gases at more efficient angles, a redesigned coolant radiator scoop that generated more thrust and less drag, and altered propeller blade geometry that reduced torque effects while maintaining performance. These incremental improvements, inspired by analyzing the backwards engine phenomenon, were incorporated into later P-51 variants, the P-51C, P-51D, and ultimately the P-51H. The result was that even though the backwards engine configuration itself was abandoned, its legacy lived on in every subsequent Mustang. The P-51D, which became the most produced variant with over 8,000 built, flew faster and farther than early P-51Bs partly because engineers had learned lessons from studying Thomas Blevins' mistake. The P-51D escorted bombers to Berlin and beyond, fought the Luftwaffe to a standstill, and helped the Allies achieve air superiority over Europe. By war's end, Mustangs had shot down nearly 5,000 German aircraft. They protected bomber formations that crippled Nazi war production. They strafed enemy airfields, trains, and convoys. They turned the tide of the air war. And buried in that success story was the strange tale of a 17-year-old mechanic who installed an engine backwards and accidentally discovered that sometimes, conventional wisdom is wrong. Thomas Blevins never knew the full extent of what he'd stumbled onto. He continued working at the Inglewood factory throughout the war, installing engines in hundreds of Mustangs, all of them correctly, as far as anyone knows. After the war, he returned to civilian life, worked as an automobile mechanic in Southern California, and rarely spoke about his time building fighters. When aviation historians finally tracked him down in the 1980s, he was an old man, his memories faded and uncertain. He remembered installing engines in Mustangs. He remembered the frantic pace of wartime production. He vaguely remembered some confusion with one particular aircraft, though he couldn't recall details. He had no idea that his mistake had sparked an experimental program, or that insights derived from studying that mistake had influenced the design of thousands of aircraft. The backwards engine Mustang remained classified until documents were declassified in the 1990s, 50 years after the war. Even then, the story emerged slowly, pieced together from scattered technical reports, test pilot memoirs, and maintenance records. Aviation historians debate its significance. Some argue it was a minor footnote, an interesting curiosity that had minimal practical impact. Others contend it represented a crucial moment when conventional assumptions were challenged, leading to real improvements in aircraft design. The truth probably lies between those extremes. The backwards engine Mustang didn't win the war by itself. It wasn't a secret superweapon that turned the tide of battle, but it was a reminder that innovation sometimes comes from unexpected sources, not from brilliant designers working methodically through calculations, but from mistakes, accidents, and the chaos of wartime production. It demonstrated that even wrong solutions can work, and sometimes work better than correct ones, if the underlying circumstances are right. And it showed that complex systems like aircraft design involve so many interacting variables that even experts can't always predict what will happen when those variables change. The Merlin engine, installed correctly, made the P-51 Mustang a great fighter. Installed backwards, it made one particular Mustang slightly faster and more maneuverable, but also less reliable and harder to maintain. The Air Force made the right decision to prioritize standardization and reliability over marginal performance gains. But the engineers also made the right decision to study why the backwards installation worked better in some ways, and to incorporate those lessons into future designs. Both decisions reflected wisdom, knowing when to exploit an innovation, and knowing when to learn from it instead. The 6 pilots who flew backwards engine Mustangs never fully understood what made their aircraft different. They knew their planes handled strangely, turned sharper to the left, responded differently in high-speed maneuvers. Some adapted and thrived. Others struggled and requested transfers back to standard aircraft. Captain Johnson, after his crash landing, returned to combat flying a standard P-51D. He survived the war with 7 confirmed kills, including the 2 Bf-109s he shot down while flying his backwards engine Mustang. He never flew another aircraft quite like it. In his later years, after the story was declassified, he gave interviews describing the experience. He spoke about the way the backwards Mustang felt alive in his hands, unpredictable but responsive, like riding a spirited horse that required constant attention. He described dogfights where the reversed handling gave him split-second advantages, moments where opponents misjudged his turn radius or reversal rate and paid with their lives. He also spoke about the constant worry that something would break, that a stressed component would fail at the worst possible moment, leaving him defenseless over enemy territory. He called it the fastest, deadliest, most unreliable fighter I ever flew, and he meant all 3 adjectives equally. The other 5 pilots scattered after the war. Some stayed in the Air Force, flying jets in the Korean War era. Others returned to civilian life. At least 2 died in post-war aviation accidents unrelated to their backwards engine experience. None of them knew, until decades later, that they'd been part of an experimental program testing a configuration born from a teenage mechanic's error. The story raises uncomfortable questions about how we understand innovation and progress. We like to believe that advancement comes through careful research, methodical testing, and brilliant insights from trained experts. The backwards engine Mustang suggests a Messier reality, that sometimes progress comes from mistakes, that accidents can reveal possibilities that deliberate analysis misses, and that systems are complex enough that even experts don't fully understand them. Thomas Blevins wasn't trying to innovate. He didn't wake up that March morning in 1943 planning to revolutionize fighter design. He was tired, confused, working under impossible pressure, and he made a mistake. But that mistake, filtered through layers of bureaucracy, testing, and analysis, contributed to making the P-51 Mustang better. Not directly, the backwards configuration itself was abandoned, but indirectly, by forcing engineers to question assumptions, to study why something wrong worked better in certain ways, and to incorporate those insights into improved designs. This is how progress often actually happens, as opposed to how we imagine it should happen. It's messy, accidental, and driven as much by chance as by careful planning. The question is whether we can create systems that recognize and exploit these accidents when they occur. The Air Force, to its credit, did exactly that. When test pilots reported unusual performance, engineers investigated instead of dismissing it. When they discovered the backwards installation, they studied it instead of simply correcting it and moving on. When they found genuine advantages, they tested them rigorously. And when they discovered reliability problems, they made the hard decision to abandon the configuration while preserving the lessons learned. That process, recognize, investigate, test, decide, and incorporate, is perhaps the real innovation here, more important than any specific technical detail about engine installation or propeller rotation. It's a process that allowed a 17-year-old's mistake to contribute, however indirectly, to winning the air war over Europe. And it's a process that remains relevant today, in any field where complex systems and uncertain outcomes demand flexibility, curiosity, and willingness to learn from unexpected sources. The P-51 Mustang, in its final optimized form, represented the culmination of countless decisions, tests, failures, and successes. The iconic bubble canopy that gave pilots unparalleled visibility. The laminar flow wing that reduced drag. The efficient cooling system that turned a liability into an asset. The reliable Merlin engine that delivered power at any altitude. Each element was refined through experience, combat testing, and engineering iteration. And buried somewhere in that refinement process was the strange lesson of the backwards engine installation, a reminder that even wrong answers can point toward better questions. By late 1944, P-51 Mustangs dominated the skies over Europe. Luftwaffe pilots, once confident and aggressive, grew cautious and defensive. The sleek American fighters ranged across Germany at will, escorting bombers, strafing ground targets, and engaging any German aircraft foolish enough to challenge them. The strategic bombing campaign, nearly broken by unsustainable losses in 1943, now proceeded with relatively acceptable casualty rates. The tide had turned. Thomas Blevins, working his shifts at the Inglewood factory, installed engines in Mustang after Mustang, each one correct, each one contributing to the stream of fighters flowing to Europe. He never knew that one of his mistakes had mattered. He never knew that somewhere in classified files, technical reports described the aircraft he'd accidentally created. He never knew that test pilots had praised its performance even while cursing its unreliability. He installed engines, hundreds of them, thousands of them, each one a small contribution to eventual victory. And perhaps that's the most fitting conclusion to the story. Not that one miraculous accident changed everything, but that one small mistake, among millions of actions by millions of people, contributed in a tiny way to a vast, complex, ultimately successful effort. The backwards engine Mustang didn't win the war. The P-51 Mustang, in all its variants, helped win the war. And somewhere in the lineage of that aircraft, in the incremental improvements that made each variant better than the last, was a lesson learned from studying why Thomas Blevins' mistake worked better than it should have. That's how wars are won, not through single brilliant strokes, but through the accumulation of countless small advantages, each one exploited, refined, and incorporated into systems that grow progressively more effective. The backwards engine Mustang was one small advantage, too unreliable to exploit directly, but valuable enough to study and learn from. And the lessons learned helped create an aircraft that truly did change the course of history, an aircraft fast enough, maneuverable enough, and reliable enough to escort bombers deep into Nazi Germany, fight the Luftwaffe on equal terms, and return home to do it again the next day, and the day after that, until the Luftwaffe was broken and the Reich lay in ruins. In the end, Thomas Blevins' backwards engine stands as a symbol of how innovation actually works in the real world. Unpredictable, messy, often accidental, but ultimately productive if we're wise enough to recognize it, study it, and learn from it. The 17-year-old mechanic who made an impossible mistake and accidentally created one of the fastest Mustangs ever built never sought recognition. He simply did his job, day after day, installing engines in fighters that would carry young pilots into combat. Some of those pilots didn't come back. Others became aces. A few flew backwards engine Mustangs without ever knowing what made them special. And the war was won by all of them together, pilots, engineers, factory workers, and yes, even teenagers who sometimes made mistakes that turned out to matter more than anyone could have guessed.